Yes. Do I have it memorized? Completely. Look at me, I'm from the West. Hey, so like we got to talk about this part. Like I'll let you guys kind of handle this part. You guys will make your own timelines and it'll be fine. But like people don't think about this part a whole lot. So we're gonna hit that, starting with kind of the earth science part. Like how does the earth form, and what does the early earth look like, and how do we get from that, which is, don't send your time machine there because it'll kill you 9 different ways, to, hey, it's nice out today. So the way the planet, and if you're wondering, like, how do we know how the Earth formed? Nobody was here. We basically know how planets like Earth form, so we can kind of extrapolate that that's how the Earth formed. Planets like Earth start as basically space junk. What makes it work is gravity, right? Because gravity isn't just what sticks you to the Earth. It's what sticks all things with mass together, or attracts all things with mass. So what you get is a bunch of, debris from the sun forming, starting to hang together in clusters, right? And that's eventually what becomes the planets. So big old cluster of cosmic debris. How do we get from that to a planet? What do you know? Did you learn this last year? Huh? It's not the Big Bang. No, the Big Bang is like the beginning of the universe. That's everything.
Isn't that some sort of explosion?
Have a smaller bang. It basically requires something moving very fast with plenty of mass to smack into it. Yeah, like an impact. Yeah, like that, except, billions of tons. Producing enough heat, because that's what happens when two things going fast hit each other, is a lot of heat is generated. Produce enough heat to melt it. That's what you need for a nice ball-shaped stratified planet like Earth. It's got to melt. Because when it melts, now gravity really starts to work. And the really dense elements in that molten ball of fire sink to the middle, forming a core, right? And the medium density stuff kind of floats to the surface and form the crust and the mantle. And the really light stuff, the least dense elements, form the atmosphere. Real different atmosphere, though, than now. Just lung melting, poisonous, toxic. That's the same thing. Yeah. Rotten egg smelling. That's the hydrogen. That's the hydrogen sulfide part. Flammable at times. Notice what's missing from there, from that list of elements. Yeah, there's no oxygen in the atmosphere yet. So even if it wasn't like poisonous, nothing to breathe. I guess if there's a saving grace, if you did accidentally pilot your time machine to 4.5 billion years ago, right before you died, take a breath, keel over. If you're facing up, the sky would be a lovely shade of pinkish orange, based on the elements we know were in the sky. That's what color it would tint with sunlight rather than blue. Beautiful. Pretty. So hot ball of death. By about 4 billion years ago, the Earth has cooled enough for there to be solid rocks on the surface, but we're still talking about like, you know, lava every few thousand steps, like just some rock.
So you said like the sky would have been pinkish orange. Is like the harmful oxygen, like not oxygen, harmful chemicals we put like in the air? Isn't that what like something to be so dirty? Like the
I don't know, maybe sometimes. Yeah, I mean, I know smog sometimes definitely. Yeah, that could be. Yeah, there may be a link there. Bad chemicals look pretty. About 3.8 billion years ago is when the Earth would have been cool enough for water to actually exist as water rather than water vapor. And at that point, fairly suddenly, the Earth would have been covered in water.
Is it normal water or is it also poison?
Oh, I'm sure it's poisonous-ish. If the atmosphere is, that means that stuff's going to be dissolved in the water as well. Yeah, don't go swimming.
What was that?
Ooh, I think it covers kind of the whole, right? Like Old Testament, New Testament. Yeah. Yeah. Okay, let me show you that. I can tell you about this all day long, but let's have some cool graphics and let me turn the recording off because it'll slow it down. So we know how planets form. That one's fairly easy. We don't totally know what happens between then and when we have life on Earth. The first question is, where do the organic molecules come from? And what I mean by organic molecules is organic molecules are molecules that are based on carbon, right? There's carbon already there, but complex organic molecules with a carbon backbone would not have been there, and then they were.
I know how aliens poured sea monkeys onto our planet.
Aliens poured sea monkeys on our planet. That
Here we are.
is certainly possible, but we don't have any evidence of that. What we do have are some experiments done by a couple of scientists named Miller and Urey. Stanley is one of them, and Harold's the other, and I can't remember which is which. Anyway, in the 50s, Miller and Urey took what we knew about the early Earth at the time and set up an experiment. Basically, they simulated the Earth's early atmosphere in a flask, like a glass flask, with some water. Because there would have been water. And then they kind of just let it sit for a few days and got nothing new. And then they thought, well, there would have been storms on the early Earth. How about lightning? And so they found a way to pass sparks through it to simulate lightning. Here's kind of what the setup looked like. Gases here, water here, heated water here, and then the electrodes pass sparks through the simulated atmosphere. What they get, surprisingly, they like let it run overnight with the sparks going through it. Come back in the morning, take a sample of the water, chemically analyze it. Amino acids, the building blocks of the protein. Yeah, which is one of the building blocks of life. Yeah, kind of cool. They made amino acids. There's a step. In the 90s, some folks decided, well, we know some more stuff about what the early Earth's atmosphere was like. They did a more accurate simulation based on more current understanding, but very similar, passing sparks through it. And they got cytosine and uracil, which you should remember as nitrogenous bases that match up in RNA. Well, cytosines in both RNA and DNA, uracils in RNA. So, big clues to, how we get those first chemicals that life is made of. They can spontaneously form in the chemicals that would have been on the early Earth, which is cool, but is not life, right? This is not living cells spontaneously generated here. And so here comes the big question. How do we get from that, some proteins, maybe some nucleotides, nucleic acids like DNA and RNA, maybe some lipids floating around. How do we get from that to cells? This is where some folks kind of tense up a little bit. Like, oh, is he about to say something against my... this is my favorite part because I get to say, short answer is we don't know. We don't know. Nobody's done it. Nobody's spontaneously created a living cell with the stuff that would have been on the early Earth. So we don't know. Maybe aliens dumped sea monkeys, like Hazen said.
Why not?
It's a really cool movie where that happened. One of the alien movies.
They dropped
Kind of, yeah. Prometheus. You see that? Starts with the alien like pouring a test tube into a river. Anyway, again, we don't get into that. Here are things we do know. If you put some random lipids, amino acids, and other stuff together and heat them in water, you can get what are called microspheres. Which are kind of cell-like. The phospholipids will do the thing where they make the double layer. They'll do that by themselves. And if they happen to catch some proteins, the right kinds of proteins inside, they make little cell-like bubbles called proteinaceous microspheres, which is a mouthful. They'll let certain things in and out and not others, like cells do. They can even store and release energy in simple ways. Maybe they were the baby step to the first cells. But they're not cells. One of the big questions that researchers have always had is, how do we get from no genetic material to DNA as the genetic material? Because DNA is kind of a one-trick pony. Like, it doesn't do much but store information and copy that information. As genetic material goes, more and more scientists agree and are experimentally supporting that RNA would be much better than DNA as the first genetic material. That cells could probably exist, and we've recently, actually, there was some pretty interesting research where they got a cell to run on just RNA. And so as a first genetic material that kind of does it all, RNA would be the better all-purpose genetic material. It's called the RNA world hypothesis, that life started with RNA instead of DNA. So that's work that's been done, microspheres look like maybe they were the baby step, and RNA looks like the best first genetic material. But beyond that, I'm not going to sit here and tell you that we know how life forms. And that is probably good for a Tuesday. I'm assuming that you have your first mission done and your packet done on the cladogram, on the Nova Labs Evolution Lab thing. I'd like you to tackle mission number 2 now. So that is your homework, mission 2. Due tomorrow, no packet to go with it. Just do it